Thank you very much. So I'm gonna discuss results that now ended up in two different papers. One is the paper that is on the proceeding here, and the second one is a longer paper that is available in the usual repositories. And this is all joint work with Robin, who is sitting in the audience. So constant function automated market makers are the centerpiece of decentralized finance in the sense that it is the most common mechanism to intermediate financial transactions. And to make sure that we are all on the same pace, let me spend a minute discussing how this works. So here I have an example of an AMM that in which you can exchange ETH for USDC. This AMM has a state, and a state is simply the size of its liquidity reserves. So how many ETH and how many USDC are sitting in the smart contract that runs the AMM. And in addition to the state, the AMM is characterized by what is called its invariant function that for our purposes collapses to this blue line. And once you have the state and the invariant function, you already know what type of trades the AMM will accept or not. And in particular, it will accept all trades that moves the state of the size of the liquidity reserves somewhere else on the blue line, and we reject those that don't. Okay, so for example, here someone showing up and proposing to buy small x amount of ETH from the AMM in exchange for small y USDC, and the trade is accepted because once you do it, you change the composition of the liquidity reserves, but you remain on the blue line. And note also that I can define a notion of price here, which will be an average price. So so how much you spend, so small y, over how many ETH you received, small x, and kind of rise over run, it will be just the slope so minus the slope of the line connecting the starting state and the arriving state, okay, this line that I draw here. That will be the average price for that trade. And I can also have a notion of marginal price, in particular what I need the marginal price after the trade. So saying, I've done this trade, now I want to do another very small trade, buy or sell another epsilon amount of ETH. Well, that will be the marginal price after the trade. And in the graph is the dotted line. And let me just point out something obvious, but it will be important later, that on a constant function AMM, the marginal price of a trade is different. So the price of a trade is different than the marginal price after the trade, okay? Now, constant function automated market makers have two well-known problems, two important problems. One is that from the user perspective, from the perspective of someone who wants to swap using the AMM, the problem is that of sandwich attack, because each trade changes the composition of the state of the AMM, so each trade, even occurring in the same block, will face different prices. This implies that if I see the state and I decide that, oh, given the state, I want to trade, and I'm a honest person, so I just send my transaction, well, an attacker may in fact put another transaction before mine, another one after mine, and make me pay more than what I was expecting to the benefit of the attacker, okay? I don't have time to explain a bit better, but I think you all more or less know what sandwich attacks are. And the second big problem from the point of view of the liquidity provider, so those who contribute the money that ends up in the reserves of the AMM, is that of, so it goes under several names: arbitrage profits, loss versus rebalancing, LVR, lever. And this I do want to spend 1 minute explaining what it is. So suppose this AMM exists next to a much larger trading value where the price is determined, say Binance, okay? And at the beginning, the price of ETH in USDC is P prime and is equal to the marginal price on my local AMM, so everything is in equilibrium. Then at one point, the price on Binance changes, say it increases to P double prime. So some arbitrageur will then naturally trade on the local AMM to bring the marginal price of the AMM in line again to P double prime, so that again, the price on the local AMM equals the price on Binance. But what is the problem is that to do so, the arbitrageur will perform a trade and move the state of the AMM, but the price that this guy has to pay is lower than P double prime. So essentially, the price that the guy has to pay is this P of X. So the price of ETH has already changed, is now P double prime, but the AMM in some sense has no way to know it, and is still willing to trade at an outdated price with the arbitrageur that can therefore trade at an advantage and make a profit at the expense of the liquidity provider who trade at a loss with the arbitrageur. This is loss versus rebalancing. Whenever there is change in price, the liquidity provider trade at a loss versus arbitrageur. And note, by the way, that those two things, so sandwich attack and this kind of loss versus rebalancing, and arbitrage profit constitute most of MEV, okay, that now we observe on chain. So what do we do in this, research project? We argue that if you batch trades before they reach the AMM, and then design the AMM knowing the trades are batched, okay, then you can essentially solve both problems. You eliminate sandwich attacks and you eliminate arbitrage profits, LVR, okay. Now, how does that work? First of all, there are many ways to enforce batching. The easiest way to think about it is just to think in terms of like an off-chain component of the AMM, like a bit like the UI, okay? So the AMM receives trades off-chain and then batches them in a sense that everything that can be settled peer-to-peer is settled peer-to-peer, and then if there is something left, what is left is going to be settled on the AMM as one big trade. And the rule is that all the trades on the same batch will have to face the same price, okay? And it's important that this AMM can be accessed only via the batch. As an extension, we consider also what happens when the batch can access multiple AMMs. Yeah, so there is batching. And I was saying, let's think of it as an off-chain component of the AMM. You could do it in other ways as an L2 or using PBS, but it's simpler to think a bit in these other ways. Okay. Now, once you know that all the trades reaching the AMM are batched, you can design an AMM, and we propose a design that we call function maximizing AMM, and this I'll discuss in a second, why you need the batch, so what it is and why you need the batch. And then we take the batch plus function maximizing AMM, and we study it in a model, a theoretical model, where there is also a larger trading value, say Binance, where the equilibrium price is determined. There are noise traders, and there are many competing arbitrageurs that are trying to exploit price differences between the different venues. And the result there is that in our simple model, the FAMM always trades at a price equal to that on Binance, which means that sandwich attacks are eliminated because it's not possible to create this kind of short-term deviation from the equilibrium price. And also that LVR and arbitrage profit are eliminated because the liquidity provider always traded the correct price against arbitrageurs. And then we have an empirical exercise. I don't know how long I will have, how much time I'll have to discuss this empirical exercise. But in short, we essentially take Binance price data and we use that to simulate, had the FAMM existed, what would have happened? In a sense, we use the theoretical model to simulate the trade that arbitrageur will have made in order to rebalance this FM-AMM, had it existed, okay? Under the assumption that there are no noise traders, okay? So this, if you want, it's a bit of a lower bound to what a liquidity provider could earn by putting liquidity into FAMM in a more reasonable scenario where there are also noise traders. So we have this simulated FAMM, and we compare the return to providing liquidity there to the return of providing liquidity on Uniswap v3, okay, on an unconcentrated liquidity position. And this is interesting for two reasons. In some sense, on the one hand, we can think about what are the benefits of this new design for AMM. And on the other hand, FAMM, the liquidity provider don't earn revenue from noise traders by design, but also don't suffer from arbitrage profit or LVR. While Uniswap v3 LPs, they suffer LVR, but they also earn revenue from noise traders. So comparing the two is also a way to add to the debate whether LPing on Uniswap v3, you are so the loss to arbitrageurs are higher or smaller to the gain from fees from noise traders. So that's kind of a contribution also of this exercise. And okay, in case I run out of time, we find that they're very similar, okay? So on Uniswap v3, it looks like the loss to arbitrageur equal more or less the revenue earned by noise traders. And this lower bound that we establish of this FAMM equals the return on Uniswap v3, which makes us think that a more realistic implementation of FAMM that also earn revenue from noise traders might outperform Uniswap v3. Okay. With a bit more details, what is a function maximizing AMM? The simplest way to think about it is as a price-taking agent that trades to maximize the product of its liquidity reserves subject to a budget constraint. Mathematically, it is this. And you can therefore then compute a demand function, essentially. So the FAMM is this agent that says, okay, if the price is this, I want to trade that. If the price is something else, I want to trade something else. Then you can ask yourself, okay, if this is the rule that the FAMM follows, and I want to exchange some amount of ETH, what is the price that I should offer to FAMM? Okay? So in short, I can invert this function and come out with a pricing function. So a price that FAMM charges for every trade that I might want to perform on FAMM. And note that, I don't know if how familiar you are with the kind of constant product AMMs, but the pricing function of a constant product AMM is exactly the same here, except for the 2, okay? So if you do the same calculation for a constant product AMM, you get something that looks very similar except for the 2. Now, these 2 might look like a small change, but it instead is very meaningful because it implies that FAMM, unlike constant product AMM, moves up the curve every trade. What do I mean? So again, let's go back to my running example. Now of an AMM where you exchange ETH or USDC, this is the starting the state of the AMM. Now this is the difference between a constant product AMM and our function maximizing AMM. The constant product AMM essentially, when there is a given price, is gonna trade so to always stay on the same curve, so the lower curve, and reach a given price. But my function maximizing AMM will instead try to move up the curve with every trade. So this is the way it will behave, okay? Now, we show that, so something you see on the graph, and we also discussed in more details in the paper, is that function maximizing AMM is clearing price consistent, meaning that the price at which it trades equals the marginal price after the trade, okay? This is just saying that you pay this much for this given trade, and then if you want to do another epsilon trade, you will still pay the same. Okay, and in fact, we show that every function maximizing AMM is clearing price consistent, and every price consistent AMM must be function maximizing. And the second important observation is that this function maximizing AMM violates path independence. Okay, I didn't tell you what path independence is, but here the important observation is that if there was no batching and you were trading with a function maximizing AMM a certain amount, you will get a better price if instead of trading the full amount at once, you will split that trade into smaller and smaller chunks, okay? And in fact, if you were able to split it in epsilon chunks, so arbitrary small chunks, you will be back to a constant product AMM, okay? So you will be able to exploit it. Now, because of batching, this is not beneficial because in the end of the day, you can split your trade, but everything is then reaggregated on the batch that treats the net as one big trade. But in some sense, this gives you a sense why this specific design is linked to the batch, okay? And why this is the case, you know, if you are an economist or a finance person, you might know the envelope theorem that says that when you are optimizing and something changes in your environment, not re-optimizing has just a second order effect on the value that you can achieve. This is a similar story here in the sense that if you have a very small trade, the difference between stay on the same curve or moving up the curve is second order. And it becomes therefore relevant only for larger trades, okay? I mean, the details are in the paper. So, okay, then, as I said, we take this FAMM, we put it in a model where there is a larger off-chain trading venue. Actually, it doesn't have to be off-chain, but okay, because we have Binance in mind, let's say it's off-chain trading venue where the equilibrium price is P star. There are noise traders that arrive and trade on the FAMM because they want to trade. They don't have particular, they are non-strategic. And then there is a large number of competing price-taking arbitrageurs that trade both on Binance and on the FAMM. It's a discrete time model, and we interpret even periods as different blocks, so where therefore the on-chain events occur, and odd periods instead are the periods in between blocks. And each odd period, at the beginning of this odd period, you always have the P star is determined, so something happened on Binance that changes the price. And then in the remainder of the period, for a certain interval of time, the batch accept trades, okay, from noise traders or arbitrageurs. And all trades submitted on the batch are observable, okay, by other arbitrageurs. I mean, by everybody, but the important thing is that arbitrageur can observe this. And then we have a proposition that obviously it's a bit more elaborate in the paper, but let me just give you the gist here. And it says that the only equilibrium the unique equilibrium of this model is one in which the FAMM always trades the price P star, so the equilibrium price, after fees. Okay, if there are fees, you have to introduce fees. But the point is, there is no equilibrium in which you have arbitrage opportunities that are left unexploited. Okay, because if there was, another arbitrageur will want to add the trade to the batch. Okay, so your only equilibrium is where this arbitrage opportunity disappear. And here is a simple model with no gas cost, blah, 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 blah. So this means that the price on FAMM always equal the Binance price. Now, in the remaining 2 minutes, we then take the theory somewhat to the data. We look at Binance prices over a certain period and over these 3 token pairs. We use the theoretical model, assuming no noise trader, to compute so essentially the trade that arbitrageurs would have performed on our FAMM had it existed in order to bring the local price in line with Binance price. It then allows us to derive how the reserves of the FAMM would have evolved, and hence the return on providing liquidity to this FAMM, like this simulation. We do this, then we compute the return of provided liquidity on Uniswap v3 for the same, so for pools corresponding to the same token pairs. And okay, yeah, the problem here is that we look at an unconcentrated liquidity provision, so we have to find a way to, we know how the number of the fee generated after each block. We have the distribution of liquidity in range at the end of the block, and we then use that to impute how many fees our liquidity provision would have earned on Uniswap v3. So then you can compute the return on that specific position. I can elaborate more later if you want. And then we compare the two. This is the result, but since I have probably like 1 minute or 30 seconds, let me just give you the number. At the end of the period that we look at, depending on the token pair that you consider, the difference between providing liquidity in one place or the other is minus 0.22, 0.03, 0.11. You can also look at the largest possible difference in value over the period between the two liquidity positions for the same token pair, like a kind of a measure of drawdown, like vaguely. And also then you get 0.3, 0.14, 0.12. So with all the caveats that one has to make to say, okay, there are no differences, because all the statistical tests that you can run are there to spot differences. It's very difficult to argue that there are no differences. But it looks to us that the difference, okay, if there is one, is fairly small. So they look more or less the same return. Finally, briefly, we have this extension in which we allow the batch to trade also on some other constant product AMM. So the FAMM can only be accessed by the batch, but the batch can also trade somewhere else, okay? And the results continue to hold there, except that the strategy for arbitrageur is a little bit more convoluted, because arbitrageur will be able to rebalance the Binance as constant function maximizing AMM and constant function AMM by essentially putting trades on the batch and then back running the batch whenever it trades also on a constant product AMM. So the strategy is a bit more convoluted there, but the results continue to hold this way. Yeah, there is a related literature, and some of you have contributed to this literature, but I don't have time to discuss it. Conclusion, I think, are not necessary. And yeah, thank you.
Thank you for the great talk. I have a good question. So there is a already existing system that kind of does something similar called Penumbra, which batches trades and does so privately. But a game actually appears for the arbitrageur. So I don't know what the conditions are for your arbitrageur theorem, but there is a game that arbitrators can play where they actually try to like outbid each other, right? And this leads to a funny thing where you don't actually reach an equilibrium price like in one batch. Does something similar appear here? And if not, why not?
So,
by the way, I guess the game is called a concave pro rata game. I don't know if you've seen it, but anyways.
Yeah, so I saw it, but I don't remember it. But it's competition between arbitrageurs is very important. It plays a very important role for our results. A competition has to be organized, and in particular, it works because of specific pricing function of the function maximizing AMM. Okay, if you had another pricing function, you would have similar things where you need so it reaches if nothing changes. So if something changes and then price stays constant for a while, you get these periodic things where every period you adjust the price and you slowly convert to the new price. But my guess is because they consider a traditional constant product AMM instead of building an AMM around the fact that the trades are batched.
Well, I think it works for any function whatsoever. So
yeah, but constant.
No, just any concave returns based on the trade size. Is that true for the constant function or your function
maximizing? No, it has to be that function.
No, I'm saying like is the quantity out for quantity in also concave?
Quantity out for quantity in, is it concave?
Like, okay, you have your constant, your function maximizing AMM.
Yes.
Right. There is a function which maps like how much you get out given how much you put in.
Yes.
Is that function concave?
Is it what? It is. I don't know. Okay.
Okay. Anyways,
I never thought about it this way, to be honest.
Thank you. Thanks for this.
Okay.
Thanks, Andrea. Haoqian?
Yes.
Go ahead.
Welcome